Hey everyone, welcome back to the channel. In this video, I'm going to go over the TCP/IP network model, how the different layers of the model interact with each other, data encapsulation, and routing. So before TCP/IP, companies created their own protocols, and these protocols only supported that company's equipment. So if you sourced equipment from different companies, you had to build different networks according to the standards of that company. Then you had to find a way to connect all those networks and get them to work. So the International Organization for Standardization, or ISO, set out to create a vendor-neutral network model to reduce that complexity. This model is now known today as the OSI model, which stands for Open System Interconnection. Now around that time, there was a group of competing researchers from various universities that set out to accomplish the same thing, and their work resulted in what we know today as the TCP/IP model. So you may be asking, why do you care? The OSI model may not be used anymore, but you often refer to concepts from it. So even though you may not use the model itself, it's still helpful to know some of the details of it. So this network model defines and references a large collection of protocols that hosts use to communicate, and RFCs, or requests for comments, are used to define those protocols. Now the model will also reference protocols that are created by other standards bodies. For example, Ethernet is defined by the IEEE, which is the Institute for Electrical and Electronic Engineers. So the TCP/IP model itself doesn't define Ethernet in an RFC, it simply refers to the IEEE standard for Ethernet. So the takeaway here is this network model is the reason why you could take a device out of the box and have it just work. And there's 5 layers to the network model. First, there's the physical layer, which focuses on how to transmit data. Then there is the data link layer, which is responsible for sending the data over the physical link. And then the network layer handles the delivery of data along the entire path from the originating host to the destination host. The transport layer performs flow and error control, among some other things. And the application layer provides services to the application software running on the host. Generally speaking, each layer provides a service to the layer above it. Let's take a look at the application layer. This layer serves as the interface between the software running on the computer and the network itself. In this diagram, we have 2 devices. There's a client on the right and a server on the left. The client is a host that reaches out to a remote device to retrieve the data that you need. Common examples of this are a computer or a cell phone. A server, on the other hand, is a device that stores the data for others to consume. We're going to take a look at how the HTTP, or the Hypertext Transfer Protocol, is used to request and return the contents of a web page. So we have a client, and that client is going to send a message to the server, and it's going to contain an HTTP header. So headers are typically used by protocols to put information that's used by the protocol itself. And in this case, the request is to get a file. So that'll get sent to the server. Now the server is going to respond with a return code and data in the payload. So in this case, it will be a 200 return code. And that just simply means that the request succeeded. There's other return codes as well, like 404 now found, but we're not going to get into that right now. So that'll get sent back to the client. Additionally, there will be further data that is sent from the server back to the client. However, you'll notice that there's no HTTP header here. The additional messages omit the header as they're not necessary. Now let's take a look at transport layer. The transport layer provides services to the application layer protocols above it. And most commonly, the protocols that you're going to see here is TCP and UDP. One of the differences between TCP and UDP is error recovery. TCP uses acknowledgements to identify lost data, and if that data is lost, the client can ask the server to send the data again. So let's take a look at an example of how TCP error recovery functions. So we're going to continue on with our example from before, where we have a server on the left and a client on the right, and there was an HTTP request that was sent from the client to the server. And we're at the point where the server is just responding for the first time. So we have our initial data, we have the HTTP response code, and in addition to that, we now have a TCP sequence number, and that gets all sent to the client. Now, as we went over in the previous illustration, there's no HTTP header that is sent with subsequent data. So now we just have the TCP header and then the data itself. However, what if there's a network problem? For some reason, this data never made it to the client. The server thinks it sent it, but the client didn't receive it. Neither one of them really knows that the data is missing. Well, when we get to the point where we're about to send the third segment, when the client receives that data, it's going to put 2 and 2 together. It's going to realize, I got segment 1 and I got segment 3, but I never got segment 2. What happened to this guy? So what the client is going to do is it's going to send a TCP message back to the server, and it's going to say, you need to send me segment number 2. I didn't get it. And that's going to prompt the server to resend segment number 2 back to the host. This example also illustrates same layer and adjacent layer interactions. So we have our TCP/IP network model, and we have the 5 layers. So an adjacent layer interaction is when adjacent layers on the same host work together. So in this case, we had HTTP and TCP working together. HTTP wanted error recovery, and it used TCP to provide that function. Now, we also have on our client machine, because it runs TCP/IP as well, the same 5 layers. Now, a same layer interaction is when the same layer on one host communicates with the same layer on another host. So in this case, we had the TCP process operating between these 2 different hosts to provide sequence numbers so that the client could tell if data was lost. Now let's take a look at the network layer. Most commonly, the protocol used here is IP, which stands for Internet Protocol. IP provides several features, most important being routing and addressing. And the most common way to explain this is using the Postal Service as an example. So say you have a card that you need to send to your mom who lives on the other side of town, and you have one that you have to send to your dad who lives in another state. For you, the process is the same. You go to the post office and you give them the card. However, for the post office, they need to handle every card individually to make sure it reaches the destination that it's going to. So your card to your mom can probably be delivered by the local post office that you gave the card to. However, the card to your dad likely needs to go to a number of post offices, and each one of them needs to inspect the card before it ultimately reaches its destination. Now, what does any of this have to really do with networking? Well, think about the functions that you sending the card and the post office perform. So you give the card to the post office and you expect them to deliver the card, but you don't need to know or really care how that's done. And the post office doesn't create the card, but they accept it, and they're expected to know about addressing and how zip codes group addresses and so forth. So the TCP/IP layers act in a similar manner. The upper layers operate where they don't know where the destination is and they really don't care. It doesn't matter if it's on the same network or if it's across the country. The upper layers ask the lower layers to deliver the message, and they expect they know how to do so. And the lower layers deliver the messages to the correct destinations. And during this whole process, routers are used to route or forward IP packets to the correct destinations. And this is similar how post offices operate in our example here. So in terms of IP addressing, there's a couple of basics that we need to go through. So first, each device needs a unique IP address so that it can be identified on the network. Addresses are grouped together, similar to how postal systems group addresses based upon zip codes. And the addresses are represented in dotted decimal notation, for example, 1.1.1.1. So let's take a look at a really basic example of how routing operates. So we're going to go with our previous example here where we have a server on the left and we have a client on the right. And that client needs to reach out to that server. But there's some new devices here. We'll call them router 1, 2, and 3. So the server needs to send a packet to that client. It's going to do so by sending the packet to the local router on the network, expecting that the router knows how to forward that packet onto the destination. Now, that packet is structured in a way where we have an HTTP header, for example. Building off of our previous example, there's a TCP header, and now there's an IP header as well. And this IP header is going to have two pieces of information. There's other information as well, but we're just going to focus on two right now. There is a source address, and there is a destination address. So the source address is going to be the server, and the destination address is going to be the client. So router 1 is going to get this packet, and it's going to look at the destination address, and it's going to compare that against its list of known routes to make a forwarding decision. So router 1 sees that I need to send this packet to router 2 in order to get this packet to the destination. When router 2 gets that packet, it's going to go through the same process. It's going to look at the destination address, and it's going to see where it needs to send that packet to get it to where it needs to go. And in this case, it's going to see that it's a locally connected network, and it's going to send it directly to the computer. Now, there's much more than this, believe me, but this is a good basic example of how routing works at the fundamental level, and we'll get into all the nuances in other videos. So next, we're going to take a look at the data link and the physical layers. Now, these layers define protocols and hardware that's required for the delivery of the data across the network. So similar to other layers, they provide services to the layer that's above it, in this case being the network layer, and the link layer details are used to send upper layer IP packets to the next host. So let's take a look at the data link layer and how it's used to send upper layer IP packets to the next host. And this is where you're going to get your first taste for encapsulation. And encapsulation is a process of adding additional information when data is traveling the OSI or the TCP IP model. So in this case, we have an IP packet, and this IP packet needs to be delivered to a destination. So what we're going to do is we're going to take this IP packet, and we're going to encapsulate it within an Ethernet header and an Ethernet trailer. And that creates an Ethernet frame. Now the server is then going to physically transmit the bits of this frame, and we'll call this guy router 1, over to router 1. And it's going to do that by changing the voltage of the electrical current that's on the wire. The router will receive those electrical signals and recreate the data. And then what the router is going to do after it gets this data, so it gets this data right here with the trailer and the header, it's going to de-encapsulate the IP packet and discard the Ethernet header and trailer. So let's take a look at encapsulation. Encapsulation is a process of putting headers and sometimes trailers around data. So as we go down the TCP/IP network model, each layer is going to add its own header to the data supplied by the layer above it. And in the case of a data link protocol, a trailer will be added as well. So if we take a look at the example we've been working on with our client and our server, we have an application that the data was encapsulated within an HTTP header. And then it was handed down to the transport layer, where TCP encapsulated the HTTP headers and data inside of a TCP segment. And then that was handed down to the network layer, where IP encapsulated the TCP headers and data inside of an IP packet. And then it was handed down to the data link layer, where Ethernet encapsulated the IP packet inside both of a header and a trailer, making an Ethernet frame. So as you can see, as we're going down from layer to layer, we're encapsulating or adding data at every step of the way. And you may notice that I reference these protocols by different names depending upon which layer we're operating in. So if we're talking about, for example, TCP, I called it a TCP segment, or I called IP an IP packet, and Ethernet an Ethernet frame. And this doesn't have to do with the protocols themselves. It has to do with where that protocol falls within the TCP/IP network model. So when we're talking about, for example, TCP and UDP, those are both transport layer protocols. So they are both considered to be segments. You can refer to them as a TCP segment or as a UDP segment. Let's take a look at the OSI and the TCP/IP layers and compare them real quick. There's many similarities between these models. For example, each layer refers to multiple protocols and standards, and effectively the bottom four layers are the same, both in name, numbering, and meaning. Now, when it comes to encapsulation, just like the TCP/IP model, each OSI layer provides services to the layer above it, and the headers and the trailers are used to encapsulate higher level data. However, instead of using segment, packet, and frame, the OSI model uses protocol data units, and that represents the bits that include headers and trailers for the layer along with encapsulated data. And the PDU is referenced by the layer itself. So, for example, an IP packet would be a layer 3 PDU or an L3 PDU. If you have any questions about what was covered, please leave a comment below. If you enjoy these tutorials and want to support my work, please like this video and share it with others. If you have the means, you can contribute to my Patreon or leave a tip in my jar. Be sure to subscribe to stay updated to my latest content, and thank you all for watching.